All right, welcome back. So, last time we got our heads around the theory of position vectors. Today, though, it's all about getting our hands dirty. We're going to jump into some classic problems, the kind you'd see in a textbook or on an exam, to really lock this stuff in.
So, you ready? Look, the best way to really get math is to do math, right? So, we're just going to jump straight in, no fluff, and solve some problems. It's the only way to see how all this theory actually works in practice. Okay, so before we dive in, let's just do a super quick refresh. What is a position vector again? The easiest way to think about it is it's just a coordinate dressed up as a vector. You've got a point, say 3, 2. The position vector is literally the arrow that goes from the origin, from 0, 0, straight to that point. It's how we turn a static coordinate into something dynamic that we can actually do math with.
Now, this right here, this is the golden rule. Seriously, this one formula is the key to pretty much everything we're going to do today. If you want the vector that gets you from point A to point B, you don't need to draw a bunch of triangles. Nope. You just take the position vector of the endpoint, B, and subtract the position vector of the start point, A. It's always end minus start. Burn that into your brain because it is your absolute best friend for these problems.
Okay, let's do this. We're jumping into exercise 9B, starting with questions 5, 6, and 7. These are going to be great for warming up and really building those core skills.
All right, first puzzle, question 5. We've got 3 points, A, B, and C. And here's the clue. The distance from A to B is exactly the same as the distance from A to C. Our mission is to figure out the possible values for this little variable Q that's hiding in point C's coordinates. So what's our game plan? It's a simple 3-step attack. First, we find the vectors AB and AC using our n minus start rule, right? So that's B minus A and C minus A. Easy enough. Second, we need their lengths. But, and this is a pro tip, don't bother with the square roots yet. Just calculate these squared lengths. It makes the algebra so much cleaner. Then, for step 3, we just set those two squared lengths equal to each other. That'll give us an equation, and we just have to solve for Q. And once you do that, what you're left with is this neat little equation. 16 plus the quantity Q minus 2 squared equals 22. And look at that. We've turned a geometry problem about vector lengths into a straightforward algebra problem. You solve that quadratic, and it turns out there are 2 possible answers for Q.
Okay, next up, question 6. This one brings in a new player, the section formula. And this thing is super powerful. I mean, it's used all over the place, from computer graphics to pinpointing a center of mass in physics. So here's the setup. We have this triangular prism, and our job is twofold. First, find the length of the main diagonal, dB. Then, we need to find the exact coordinates of a point N that splits that diagonal up in a 2:3 ratio.
Part A is pretty standard stuff by now. You find the vector dB. How? End minus start, so B minus D. Then you use 3D Pythagoras to get its length, which, nice and clean, comes out to 25 centimeters. Now for part B, we get to use our shiny new tool, the section formula. All it really is a fancy way of taking a weighted average of the 2 endpoints. You plug in the numbers and it spits out the exact position vector for our point N. All right, question 7. This is going to feel a little familiar. It's a lot like question 5. We've got 2 vectors, OP and OQ. Both of them have this unknown variable A baked into them. And just like before, we're told their lengths are identical. Our job, find A. So the setup is key. And we're going to use our trick again, right? We'll work with the squared lengths to dodge those annoying square roots. So you calculate the squared length of OP, the squared length of OQ, and set them equal. This gives you the equation you see here. Now, at first glance, it might look a bit messy, but check this out. See that A squared on both sides? They're going to cancel each other out, making this whole thing way simpler to solve. So you expand that bracket, the A squareds disappear, and what are we left with? A super simple linear equation. 29 equals 11 plus 2a. A little shuffle and boom, we get our answer. A has to be 9. Okay, nice. We've definitely got the basics down. Now let's ramp it up a notch and tackle the last 2 questions in this set, 8 and 9. These are a little more advanced. So question 8 brings a new idea to the table, collinear points. All that means is that 3 points, in this case the origin O, P, and Q, all lie on the exact same straight line. That one little detail is everything. It's the clue that unlocks the value of K and lets us figure out the distance between P and Q. Let's walk through the steps. Step 1, and this is the big idea. If the points are collinear with the origin, it means one vector is just a multiple of the other.
So vector OQ is just some number times vector OP. We compare the components, and that lets us solve for k, which is -1/2. Step 2, plug that k value back in to get the actual vectors for OP and OQ. Step 3 is easy. We want the vector PQ, so we do OQ minus OP. And step 4, the final move, is to find the magnitude of that new vector, which gives us the square root of 261.
And for our last problem from the textbook, question 9, we get a little story. It's about an ant who leaves home and goes on a journey. It makes 5 different moves to find some food. The question for us is, what's the single straight line path to get back home, and exactly how long is that path?
So these are the ant's 5 separate moves, each one a vector. To figure out where it ends up, all we have to do is add them all together. It's that simple. Just add up all the I components, then all the j components, and finally all the k components. That will give us the ant's final position.
Okay, so when you add up all those numbers, you find out the ant is now at the position 1380 relative to where it started. Now be careful, that's the vector to the food. To get home, the ant needs to go in the exact opposite direction. So the vector home is just the negative of that, -13, -80. And for the grand finale, we need the actual distance. That's just the magnitude of our go-home vector. So we find the square root of -13 squared plus -8 squared, which is the square root of 233. But wait, the problem said each unit is 10 centimeters. So we got to multiply by 10. And that gives us our final answer, about 152.7 centimeters. The ant is home. Fantastic job. That was the tough part. Now you ready for a little speed run? We're going to do a rapid fire review, what I call the exam gauntlet. I'll throw out a question, you think of the answer. Quick and dirty. Let's see how sharp these skills are. Ready? Let's hit it. Okay, question 1. Midpoint of A and B, just average them. That's 3.55. Boom. Next up, vector from A to B, n minus start. B minus A gives you 2, -2. Simple. And last one, point C divides a line in a ratio. That's a job for the section formula. And the answer is 3.2, 2.2. Done. See? This is the kind of stuff you want to be able to do in your sleep come exam time. So there you have it. We've gone through the mechanics, we've solved the problems. But what's the big picture here? Why should you care? Because what we just did, manipulating these little arrows on a page, this is exactly how scientists and engineers modeled the real 3-dimensional world. Whether it's plotting the course for a rocket, calculating the stresses on a skyscraper, or tracking a subatomic particle, it all comes down to these fundamental principles. It's not just abstract math, it's the language we use to describe reality itself.